Okay, it's 12 o'clock on the nose, so we'll get started. Hello, everyone, and welcome to DFI's Impact webinar. DFI's Driven Pile Committee hosts this webinar to highlight innovative developments, current practices, and case studies focused on driven pile foundations. If there's anything pile related that can benefit the industry, we want to help get that information out there. My name is Travis Coleman, and I work for GRL Engineers out of our Chicago office. So quick housekeeping on the next slide. There you go. So you'll all automatically be muted during the presentation. If you have any questions, please use the Q&A function within the website. I'll monitor those and ask questions for both of our presenters at the end of the presentations. So today we have two excellent presenters. First, we have Chernauskas, President of Geosciences Testing and Research. He'll be presenting on recent trends in driven pile foundations in New England. He'll cover some non-traditional piles and some high capacity piles, along with some installation issues. And our second presenter is my GRL colleague, Alex Ryberg, Vice President of GRL based out of Philadelphia. He'll present on another form of non-traditional piles, ductile iron pipes. So with that, Les, it's yours.
All right, thanks, Travis, and thanks for DFI for inviting me today to speak about my topic. As Travis said, I'm president of GTR, and I'm going to be presenting recent trends in driven pile foundations in New England. It will be mostly focused on the Boston area, southeastern Massachusetts, and Rhode Island, but we use New England to make it simple for us. See if I can advance the slide here. The general outline will be, I'll go into the introduction, talk a little bit about pile driving safety, because you can never have enough safety regarding piles and being safe around the site during pile installation. I'll talk about the two trends and what they are. One is on non-traditional pipe pile types with a case history, and the other is on high capacity or really high allowable stress H pile foundations with a case history or two. And then leading up to that is what really controls the allowable pile loads with regard to the high stresses. And then quick conclusions. So just a little bit about our company. We were founded in 1995 as a geotechnical construction engineering and consulting firm. We have offices in Mass and New York. And we collaborate a lot with FHWA, DFI, and UMass Lowell on various research topics. And we perform various types of geotechnical services related to deep foundation design, testing, and engineering. And along our experiences, we've done a lot of driven piles in and around the Northeast. Just a basic summary of what a driven pile foundation is, or any deep foundation. It transfers the structural loads through soft ground and or water, if it's in a marine application, to competent underlying soil strata. Why use driven piles? Well, they have high productivity and they're cost effective. You can put a lot of piles in per day, and they're dependable. Everyone knows the phrase, a driven pile is a tested pile. So if you get a blow count and you roughly know the energy when you drive a pile, you know the capacity, or at least you have an idea of the capacity. And it's very repeatable. Once you get going on a pile job, usually it gets to be pretty monotonous if you're driving hundreds or thousands of piles, because they usually go in, pretty uniformly in the same, for the most part. A lot of engineers and contractors have local experience and extensive databases and on their practice in their particular area. And of course, the equipment's readily available. Sometimes not only pile driving subs and specialists put the piles in, but a lot of general contractors would also try to put piles in, particularly for bridge foundations. So I just want to talk a little bit about pile driving safety. It's always good practice, right? a lot of us work around pile driving rigs and installing piles, whether as an inspector or testing in some manner. So the biggest thing is, keep away from the rig, always keep to the side of it, because been on plenty of projects where some piece or debris falls off the pile. Usually it could even be a 4-ounce bolt or something, but that falls and hits you from 100 feet. That could be an issue. So, and then there's worse things that could happen. The pile can fall out of the leads. So it's always good to be off to the side as much as possible when, working with either inspecting the blow counts or testing the piles. And leading up to that is be aware of the equipment that's around you, particularly when you're working between piles. We've had engineers out on sites before where they were focused on testing and not really paying attention to what's behind them because they didn't maybe know that a laborer or a dock worker came behind, started welding and torching a pile, and they've fallen, within feet of our guys. Now, that requires everyone to be safe, but just you can never be safe enough and always have to have your head on a swivel. And of course, eye protection, ear protection, and wearing a vest over water. So the two major trends that I'm going to talk about today are what I would call use of non-traditional or innovative pipe pile sections. These are basically trademark adaptations to lower portions of the pipe to increase its load carrying capacity. It keeps the pile length shorter, or it generates more resistance at a similar depth than a standard, say, pipe pile. So that's the first topic, and we've used these pile types in and around a lot of sand and marine applications. The other trend that I'd say over the last 10 years, plus or minus, in New England area. The other one is high allowable stresses or capacities, I put in parentheses there, for H piles, meaning, using design stresses 20 KSI, 22 KSI, 21, which are traditionally higher than, the standard 16, 15, 17 KSI. And there's some issues that happen when you approach those stresses that you need to consider. And that's becoming a big trend in the Boston area, say for 14-inch H sections. They're putting 200, 250, 300 ton design loads on these piles. Obviously, they have to be driven to rock. So because of that, you need a more detailed evaluation and understanding of the soil and particularly the rock conditions. The reason why engineers and designers are trending this way and trying to, use these 20, 22 KSI design stresses is they have increased confidence in the quality control and the testing that's available now with PDA and, the load test data, and also their experience with the projects as they do more of them. And hydraulic hammers now provide information and feedback. They're larger, but yet they don't weigh as much as the old traditional hammers. So you can generate and get a lot of energy into these piles so that you can drive into the higher loads. It could also be a smaller H pile, like an HP10 or HP12, just using the higher stress. It just would be driven to a lot higher load than you might typically expect. And because of that, which I'll talk about later, is you could have drivability issues. So a lot of these high capacity loads for these 250, 300 ton design load H sections the pile capacity is controlled by the rock quality and the drivability. And I'll talk about that a little bit later, but first I'll talk about the innovative or non-traditional pipe piles. The first one is spin fin piles. Now these are basically used in marine applications, a lot of offshore dolphin structures, wharf structures, mainly because they have to deform a decent amount to fully activate and take advantage of their resisting capacity. So you won't really find them in a bridge structure or a building because they have to, they're more, their tolerance for movements are less. But they can generate high capacities in sands, even loose sands, compression and tension, with a shorter penetration than a traditional pipe pile. You can install them with conventional hammers, typical diesel hammers that are used offshore a lot. And the rule of thumb we use is 20, 25 feet, somewhere in there. If you could save that on a pipe pile with the use of this by keeping it up shallower, then that you start to see economic benefits. The other way to look at it is if you drive it to the same depth as a pipe pile, it'll probably generate more capacity. So then you don't need as many piles. So you could do it either way. The big thing with these piles is you have to put tabs or shear studs at the top of the pile and the connection with the cap, so that when the cap is poured and the cap is loaded, the pile wants to spin, but it can't because it's locked into the concrete, and that also increases. That's where the full resistance and capacity of the pile is activated. So one of the case history I have here is at a project in Oak Bluffs in southeastern Massachusetts, and it's in Martha's Vineyard off of Cape Cod. And the Steamship Authority is a big user of these piles because they have a lot of marine facilities and offshore structures, dolphins and wharfs. So they have many years ago, I think it was in the early 2000s, we convinced them to start using these piles on their projects. And in the Cape, it's basically a medium dense sand profile. In this project, we used 16-inch spin fin and compared it to 16-inch closed-ended pipe, drove them and did compression load testing, tension load testing, and PDA on both pile types, spread them around the site to get good, a good sense of how they would perform. And on the left here, you could see it's a shop drawing basically of the spin fin portion on the lower part of the pile. This is about 5 feet, could be 6 feet. It's put at a slight angle. Usually they're an inch thick plate around a foot wide that is on a slight taper as it goes along the pile to create the fin effect. And you could have 6, 7, or 8 of them, depending on the diameter of the pile, to help act as an anchor when they're driven. And during the course of driving, these piles will probably rotate one full rotation as they go in. And these are some more photos. This is the actual full port facility. The Dolphin is here. These were actually on 20-inch spin fin piles. Oops. Sorry, having a little problem here. All right. This was on 20-inch spin fin piles. This was on these 16-inch piles that were in the wharf. And the unusual aspect of trying to test the spin fin pile is the load frame has to simulate that locked-in condition for the pile head. So you have to put the piles on a batter and then connect the pile top, which really kind of resists torsion and the lateral force. So the frame is a little more complicated so that you can fully take advantage of the test of its full capacity. So these were the results of that project in Oak Bluffs. The 16-inch spin fin and the closed-end pipe here in this table. The penetrations were about half of the pipe pile. They developed the same rough capacities in compression, and in tension, they actually had a decent amount more capacity. So what they ended up doing is saving a lot of splicing that had to be performed on the project, and it saves basically the splicing saves a season in the construction process, because usually these are over 2 years or 3 years, and that's a big deal for the Steamship Authority because it disrupts their ferry traffic much less than having to do it for 3 full construction seasons. The plots on the bottom here on the left and the right, they're just the cyclic load tests for the compression tests on the spin fin and in tension and compression. And we use Davison's criteria. I don't know how easy it is for you guys to see this, but this dashed red line is Davison's. It's crossing around 135 tons. And so is the cyclic loading and reloading, pretty consistently the same value, around 135 tons in compression. Similarly here, the capacity on the tension is around 75 tons. So that's the spin fin case history. The other pile that's been used or we're trying to use more of in the New England area. Some of these piles, by the way, whether there's spin fin, which is used heavily in the Northwest, PND Engineers had originally used these piles, and they do a lot of their work in the Seattle area and in Alaska. So they've used these piles for many years up in that part of the country. And I'm not familiar with how much it's used elsewhere, but in New England, it's not used very frequently until we started using them with the Steamship Authority. Similarly, with taper tubes, they're used heavily in the New York area, JFK and LaGuardia airports in New Jersey. And they basically have a tapered section to them over the lower 25 feet. I don't know how much they're used in other parts of the country, but I know in New England, they were not used very often. And we had tried it on a project in Providence that I'll talk about in a second. The advantage for the taper tube piles is because of that taper, you can get a significant increase in capacity of over a pipe pile. And then the shaft, it's very useful in granular soils for both compression and even tension. We've tested them in tension. They're installed again with conventional pile driving equipment, and they have a reinforced cone tip to help drivability. And they are a higher cost than regular pipe piles. And my rule of thumb again is around 20 to 25 feet. If you can save that penetration, then that's when they become economical. Or you just will get more capacity out of them for the same depth, so you could have less piles. So the project that we worked on here, my colleague Seth Hamlin was involved in this. In Providence, Rhode Island. It was for Rhode Island DOT 610 interchange in Providence. This was the first application or use of the taper tubes in New England that we know of. We have done test piles with them, but they're not commonly used as far as we know. And we just recently have had another one used out on the Cape for a bridge structure. In this particular project here in Providence, these was medium dense to dense sand profile, kind of two different areas of soil conditions. Originally, micropiles were proposed, and the taper tube was a value engineering alternative. So in order to investigate the feasibility of it, the contractor, who was Barletta, they were interested in this, so they allowed us to perform compression, tension, and lateral testing, also PDA on these piles. We also compared the taper tube to closed-end pipe piles, both 16-inch diameter, just to see, what the differences would be, what would be more cost-effective, because it was the first use that we know of them in the area, and compared that to the micropiles. Here's on the left is a shop drawing of a taper tube. It has a telltale pipe in it, but basically over the lower, in this case, 23 feet, but it could vary between 20 and 25 feet. Generally, the taper will vary. Usually it's an 8-inch tip. And obviously it's connected to the pipe, standard pipe. These are the results at that project. The piles were generally driven to 2 to 4 blows an inch with around 25 kip feet of energy transferred based on the PDA results. At a 50-foot penetration, the taper tube piles were able to generate 215 tons in compressive capacity, while the pipe piles at 70 feet generated around 180 tons. And these are the load test plots down here. You can see this, the taper tube has a general plunging, but it's a gradual plunging. And if you use Davison's right here, that comes out to about 250 tons. If you can see this, this was the assigned ultimate capacity of the taper tubes. And there's a very distinct plunging behavior for the closed end pipe, and that's around 180 tons. So at a shorter penetration, the taper tube was able to generate, 30% more capacity or even more. So because of that, there was less footage than the pipe would have, and we're able to use less taper tube than pipe piles. And it saved 18 months on schedule compared to what the micropiles would have taken. Well over $1 million of savings to the project. So that was the innovative or alternative pipe pile sections. Now we're talking about a second trend that talks, it's about high allowable stress H piles, high capacities. And in order to establish these stresses, they're from the IBC code. They're based on structural limits, not geotechnical limits. Usually it's 35% of the yield strength based on this section in the IBC code. You can go higher. There's a justification for that for higher stresses. You can go up to 50% of FY. There are limits on these stresses that I'll have on the next slide, but the code says if you do a soils investigation and testing, you can go to higher stresses. So it's really a comfort thing for the engineer to be able to take advantage of that. Of course, you could do dynamic testing to help guide in the selection of the static test pile, to look at variability around the site and to refine the driving criteria. These limitations, I use just Connecticut and Massachusetts as examples here, but 35% of FY with a limitation of 24 KSI in Connecticut and 16 KSI in Mass. This 24 KSI, I just checked the code compared to what it was several years ago, has been an increase. I think it was 17 or 18 KSI. So there, Connecticut has acknowledged the use of allowing a higher stress just under normal use of the H piles, 35 FY. But if you do want to go to higher stresses, you can go to 50% of FY up to 32 KSI. Well, I've never seen anyone use much more than 24, 25 KSI on a pile. That's a pretty high design stress. I also threw the pipe piles in here, but on this case, we're not really discussing those in terms of high stresses. Just some photos of H piles. And as I said before, the increased confidence in quality control and load testing has allowed engineers to become a little more comfortable using higher stresses in that 20 to 22 KSI range. And the bigger hydraulic hammers, I know this is a diesel here, but these two are hydraulic hammers, and they're much more efficient and in my mind can drive the piles with less damage under the same provided energy. This is just a plot of a summary around the Boston area of use of these high allowable stress or high capacity H piles, where the design loads were 200 to 300 plus tons, around 20 KSI, 18 to 21 KSI used for the design stress. They were generally driven to 10 to 20 blows an inch with 50 to 100 kip feet of transfer and energy. So you can see the big range of these piles is right in here between 800 and 1,000 kips ultimate capacity. There was one project here in UMass Boston where the piles they really took full advantage of the pile sections and drove them to 1,400 kips plus of ultimate capacity. I think these had over 300-ton design load. So now what really controls the allowable load or the allowable stress that you can pick for the pile? At this point, it really comes down to the quality of the rock or the soil, and can it support the loads that you're looking for? At these loads, soil will not really provide you the loads that you're looking for. It has to be rock, and even weathered rock sometimes can't support the higher loads, at least in the Boston area with the argillite performance. I have an example of that shortly. And then the other thing is the drivability, about how it affects how high you can really go with your allowable stress and your loads. You got to be able to get the pile in without damage, and you have to consider the combination of the soil rock conditions, the pile geometry, and the hammer compatibility. And I have an example of that as well. Just a little bit more on the soil and rock conditions. So because it's rock and it's at the tip of the pile, all the capacity and most of the performance is controlled near the tip. For example, hard rock, the allowable bearing values in the Mass code are 200 KSF. And if you use a factor of safety of 3, Get to 600 KSF, that's around 4,000 PSI. So you're talking about the strength of concrete, you know, and with granite, you can have 3 or more times that strength. So when you're driving hard rock, you know, these H piles, if they hit something like hard granite, they'll stop. And you'll be able to generate these capacities as long as you don't break the pile. Weathered rock, on the other hand, has significant lower bearing capacity when you consider the higher loads that you need to drive them to. So it can penetrate a decent amount into weathered bedrock. So therefore, when you're doing your coring and selecting, you know, your geotechnical subsurface program, you really now need to take rock cores where you may not have done that on pile jobs in the past, because you will be driving and need to consider the performance of the rock and the quality of the rock in this case. This is an example of PDA results for driving into rock, weathered rock. It was an H pile in Boston. And this is pretty typical when we're trying to get, you know, 1,000 kips or 800, 900 kips in capacity. The general layout of this drawing is, this is the penetration on the y-axis. The energies in the blue is we pretty much drove these piles to 90 kip feet, 90 kip foot of energy. And in the till over here, with that energy, it's 2 blows an inch and generating around 400 kips in capacity. As you drive deeper and encounter the weather rock over here, you get to 5 and 6 blows an inch and approach 700-800 kips in capacity. And it just keeps driving with a slow increase up to 10 blows an inch before we stopped and hit something harder down here. So this weathered rock had a significant driving distance in it. It was weathered argillite. And one thing to note, you can see here that this is 30 KSI in driving stresses at the pile top, pretty much consistently hit the rock and it jumped up a little. But this is the tip driving compressive stresses. And as it hits the rock and penetrates deeper, they actually drop off a little bit because of the significant friction that's developed in the weathered rock. So it's just an interesting note to point out on the drivability of these H piles. And I just put some examples of some load tests that have been done over, you know, these various projects. For soft rock, you know, you have this behavior, you actually have pretty, you know, pretty good creep. This is the tip of the pile here. This is a static load test plot of load versus on the horizontal axis and displacement on the vertical axis. And you could see this pile basically plunged through to failure during the creep hold because it's soft rock, as opposed to hard rock on the right, which it's hard to see. I know there's a lot of lines, plots here, but it's basically elastic down and back up with very little creep. So they follow the elastic line. And this would be typical of what, you know, hard rock would provide during a load test. Same thing here. This was hard Boston argillite where we tested up the UMass Boston to 1,400 kips. This was a telltale, so it's a tip movement. But here's just the 3 pile top dial gauges. And another important note is the loading of these piles. Again, this was to an ultimate load, but it almost moved 4 inches down here. It's 4 inches of movement, all elastic. So continuing on with this, what controls the allowable load related to drivability now. The pile geometry significantly does play a large part in the overall performance of the pile as it's driven. The length and area contribute to this. And, you know, if the length gets longer, the pile becomes less stiff, loses energy and becomes harder to drive. And as the area becomes bigger on a pile, it becomes heavier and therefore it's easily drivable. You can get a bigger pile driven to a lower blow count to the same capacity. And I have a theoretical relationship with the wave equation to kind of show this effect. So besides pile geometry, it's also hammer size. You know, short piles on rock, the driving stresses control. Longer piles in weathered rock, then the energy becomes attenuated and it becomes less stiff. So you could have a difficult time proving capacity just because of the higher blow counts and losses of energy. So for given energy, both the pile stiffness and the mass can influence the blow count versus capacity. If you have too much energy, you could have pile damage, while too little, you may not develop or prove the resistance depending on how you're testing the pile. Some of these projects now we're just doing PDA and no load tests, either through a waiver or just they've slightly increased the factor of safety when there's just dynamic testing. Of course, when you talk about H piles, you have to have the slide of pile damage. And I just put this in there because I know it's interesting to see. You never know what you get when you put the pile in the ground. And these are some photos we've had of piles. Everyone knows the photo that Felenius has of the H pile driven down, and it comes in a U right back underneath the car and pushes it up out of the ground. So this is just a corkscrew on an H pile, complete damage, and a bending on an H pile over here. And of course, this is the new pile that I want to patent. It's called the strain hardened Twizzler pile. I don't know if you can see that. I had to put this in there because I don't think we'd ever be able to repeat this. I don't know how this happened. The pile was in the helmet, and it twisted below grade and started to shift, and everyone's wondering what happened. We had dynamic testing on this pile. You couldn't really see this because there's no real acute change in the pile properties, but because it was moving, they pulled it out, and this is how it came out. So you never know what you're going to get when you put your piles in the ground. I'll try to go through this quickly. I know I have a few more minutes. Related to what I talked about on pile geometry, this was just an exercise, a theoretical exercise we ran with the wave equation. And for example, we'll start with area. It's in red here. This is 20 inches, 30 square inches, 40 square inches, 50 square inches. So it's just an increase in area on the x-axis, and then blow count is on the vertical axis on both sides. So if you start with an area, say, of 30 square inches, this could be an HP 14 by 102. You have 220 blows per foot. This was for a given pile length, a given energy, and a given, I think it was the same length, same energy, same capacity. And then we put say, for example, multiple other areas in there, pile types. So at 220 blows per foot for this 14 by 102, by increasing that pile, keeping the length the same, the capacity same, and the energy the same, that's around 35 square inches. It drops it down to 100 blows per foot. So just that extra 5 square inches, the weight related to that had dropped the blow count drastically. Again, this is a theoretical exercise, but my point is to show that if you're always worried about the drivability, to go up one size in a pile may make a big difference in how you can get it in the ground. And similarly related to, it's the inverse relationship where you increase a pile length and keep everything else the same area, same capacity, same energy, but just make the pile longer. You basically have, the blow count goes up as the length goes up because it becomes less stiff. So this is just all a theoretical H pile exercise in WEEP. I have more discussion, which I'll probably skip through quickly here, but this is related to the energy and hammer compatibility. On this case, it's just, real quickly on the bottom, the capacity here is increasing on the x-axis, and on the y-axis, it's the compressive stress. So you could see that as, this bottom dashed line is 35,000 or 35 kip feet of transfer energy. Here's more energy. This line, it's the relationship between capacity and driving stresses for 50 kip feet, and then same for 65 kip feet. All this shows is, as you would expect, as you go up in capacity and you go up in energy, the stresses are going to go up. So it's just a theoretical exercise, the same pile. And then you can also do it for blow count. This is really a bearing graph turned up on its side. But essentially, as you increase your energy, you have blow count here and capacity on the bottom. As your capacity goes up, and if you have a certain energy, your blow count will go up as your capacity goes up, correct? And as you keep increasing the energy, you'll be able to get more capacity. So for example, if you wanted to say, what's it going to take to get 700 kips using this hammer of 35 kip feet, that's going to take 250, 240 blows per foot, basically refusal. If you increase your energy and go by 50%, you could drop that to 100 blows per foot. for the same capacity of 700 kips, just by going from, almost 50% more energy. I just combine these two here. That's too confusing to go in, but I bring this slide back up because this was a load test done in Boston. Again, I showed you earlier about the drivability of the H-pile through the soil profile. Well, I just bring this up again to show that this is the load test related to that. And what we're looking at here is two load tests that were performed. The blue load test was the first load test on the pile that I just showed you on the last screen. It was driven to around, I think, 10, 12 blows an inch, and with about 70 to 80 kip feet in energy. And it basically crept through Davison's at around 440 tons. So the engineer wanted 450 tons, and this was a big deal because obviously the pile failed, but they had to rerun the load test. What they did was they got back on the pile, got on with a bigger hammer at 100 to 105 kip feet of energy, redrove it to refusal. It went another few inches. It didn't go very deep. Reran the load test, and that's in the red here. And basically you got 460 tons. It plunged through the Davisons. So it's essentially the same load, driven to much more energy and a much higher blow count. And the reason why I present this is because this argillite wasn't going to provide much more than 450 tons. I mean, that was the limit, no matter how hard you put it in there and how hard you drive it. So it's just my point of one of the projects we've had where we've seen that the rock will not, you can't squeeze blood out of a stone, right? Literally. So that's all you can get out of this pile is 450 tons. So that's pretty much it. In conclusion, I'd like to say that for H piles, when you drive into high capacities and high allowable stresses, you'd like to consider, the rock quality, how it's weathered, fractured, the jointing. So you need to focus on that a little bit on your boring program and get some cores. Your pile geometry, the area will really help out if you're on the borderline, and you can, if you don't want that stress to be 20, 22 KSI, and you go up the next size, drop it down to 18, maybe that helps immensely in terms of its drivability. And then the hammer requirements, obviously, to balance the stresses versus the blow counts. That's related to the high stress piles, right? And then for the innovated taper tube and spin fin pile types, the rule of thumb is when you can save 20 to 25 feet in length, they become cost effective, or you can generate more capacity and put less piles in. You determine all that during the test program. The other big aspect of these piles is if you could keep the length shorter and reduce a splice, it can significantly accelerate the schedule, and there's huge cost savings in that. So just to reiterate, in Rhode Island at 610 project, that was the first use of taper tube that we know of. And for the spin fins, the Steamship Authority routinely use them around their southeastern Massachusetts facilities because it's pretty much a medium dense sand, and it's hard to get much capacity out of those without driving the piles to basically to China. So in the end, I just throw this out there. If a certain pile type has not been used in an area, or it's new and you want to take advantage of high stresses, or you want to use an innovative soil pile type, spin fin or taper tube, there's a possibility that the load test fails, or you won't get what you're looking for. You may not find that out during the construction load test program. And then who owns the risk in that case? It's the owner's project, right? They own the soil. So you really need to consider that, either do a design phase test program if the project's big enough, or just consider that you may not get exactly what you want, and that you might have to consider downgrading loads or adding piles. And that's pretty much it. Thank you very much.
Thanks so much, Les. That was excellent. If anyone has any questions, please use this Q&A box within the Zoom meeting. And like I said, I'll pass those on as time allows at the end of the presentations. So next up, we have Alex Ryberg from GRL with Ductile Iron Pipes. And go ahead, Alex.
Thanks, Travis. That was a great presentation, Les. It feeds a little bit onto the same topic here. So I'll be doing a presentation about using dynamic testing, which we've used for many decades now, on a ductile iron pipe application. So first we'll jump into just a outline, very briefly talk about pile driving, dynamic testing, basic theory, some of that Les already covered. We'll talk about what is ductile iron pipe, go into a case history and compare some dynamic and static testing results and discuss some takeaways and further discussions for it. So starting off, we've been driving piles for a while. In 2000 BC, there's records of the Egyptians, the Romans, Chinese, Mesopotamian empires using piles. Venice and Amsterdam were installed and still standing, installed with timber piles. And just to put that into perspective, the profession as we know it of civil engineering came about in the 18th century. So we've been doing pile driving and installing piles in the ground way before we understood physically what's happening. So it's a trusted method, certainly. And continuing with that timeline, ASC was founded in 1852. Engineering News Record formula, which is sometimes still used nowadays, was established in 1888. The French strain measurements were 1920. Carl Terzaghi wrote his book on soil mechanics in the 20s. And in 1948, E.A. Smith developed what is essentially the wave equation to formulate pile behavior and soil interaction using springs and dashpods. And in 1968, the first electronic dynamic testing system was developed by within a research project in Case Institute of Technology, which eventually turned into what we know as the PDA now. And in the 70s, the wave equation for program was introduced through assistance of FHWA and New York DOT, which allowed everybody, kind of the general public, to use that analysis as well. So when we're driving pile, we have a load that's applied from the ram, which is usually a hammer. The pile is compressed, and we have a measurement that's obtained from strain gauges that measure the strain, which gives us the total force over time. We also have acceleration measurements that are measured with an accelerometer. We take the integral of the acceleration, we get velocity. So in essence, what we're doing is we're filtering out the dynamic portion, which is from the acceleration record, and we get left off with the static component, which we hope is the way the piles will behave under a service condition. We can test any pile type, uniform piles, concrete piles on the left. We could see square, cylindrical piles. We have timber piles. Those are, well, maybe a little non-uniform. We have steel piles, pipe piles, H piles. On the right-hand side is a fiberglass pile that we tested recently. As last mentioned, we also have non-uniform piles, spin fin piles, combinations of different geometries, same material, sometimes composite. And we've also been testing piles that are not driven, or either drilled or torqued or spun in place since the 1970s. This is a helical pile that was installed just outside of Philadelphia with our drop hammer that we were impacting and did dynamic testing on a few years back. We've also tested micro helical pull down piles, which are on the left. Those are partially grouted with helices. And we also can test drilled shafts. All of these are foundation elements, deep foundation elements that are installed without an impact hammer, but they can still be tested by applying an impact to them. So let's look into ductile iron pipe. Essentially, it's cast iron, which is a combination of iron, carbon, graphite flakes. And the properties that you get from that material is you get really high strength, but it's brittle. So if you put those materials or elements and add a couple more into a centrifuge, the crystal structure changes to be a bit more spheroidal. So it has all the same material strengths, but it also allows the material to be ductile and more flexible and not as brittle. And so there's different manufacturers for ductile iron pipe. We tested one that was manufactured by Duroterra. Each section typically comes in 5-meter lengths. The nominal length is a little bit longer to include the socket and the spigot. There's different diameters, as you can see, ranging from 3.86 inches to 6.69. And the wall thicknesses also change for each of these diameters. So it also ranges from about 1/4 inch to 1/2 inch. These piles can be driven open-ended or closed-ended, just like a typical pipe pile. If you want it to be a friction pile, or if you want it to be more of an end-bearing type of component, where you want to close the end off to mobilize the resistance or protect the tip, you can also have a pointed end or a rock point, similar to a rock crusher plate if you've seen those in the field. And each section basically has a spigot and a socket. So when one section is driven into the ground, the next section gets placed inside of the bottom one and essentially wedged in and impacted. And when it's impacted through friction, we see reportedly a cold or friction weld that's formed. This essentially creates a splice of that of the two sections, and also increases the stiffness once it is combined or welded together. So you have an increased area and stiffness at that depth, which is not the weak point of that pile anymore. So this is a typical setup. You could see the different sections laying on the ground there, each about 5 meters long. The contractor would pick up each section, drive it into the ground. Once it's down to within 1 foot or 2 above grade, the next section gets placed, and a hydraulic breaker, which is mounted on an excavator in this case, which I think is the typical setup, is used to impact and drive these piles. So the project that we were involved with had a required capacity of 120 kips. This is the larger diameter pile size, with the wall thickness was somewhere in the middle range. And the engineers estimated that it would take about 2 to 3 sections to reach the end-bearing stratum that they need for the required resistance. The soils mostly consisted of soft fill material in the upper layer, and then poorly graded sands with N values, as you could see, quite variable from 5 to 166. And below that, occasionally you hit shale. So there's a little bit of variability here. So that contributed to the uncertainty of how many sections would be needed to reach there. So this is the job site we were on, and typically these piles are installed with the hydraulic breaker running. And if you've ever been on a job site where they're doing demolition work with these breakers or jackhammer, you know they run pretty quickly. So what they do is they measure how much time or the penetration rate it takes for that pile to be installed. So for example, it takes a minute to install 1 meter of the pile length, and then they could correlate that on a chart that's provided by the manufacturer to a bearing capacity. So the goal of the testing that we were called for is to attempt to perform dynamic testing on these piles during installation, which, as far as I know, has never been done. They've been tested after the fact, statically and dynamically, but never during installation. So taking a look at some sample data that we got, we have a graph here, which is a little difficult to see, but in the upper portion of the graph here, those are the 4 strain gauges. So we've doubled up on gauges. And on the bottom are the 4 accelerometers, or the velocity records. So starting from the bottom, we could see all the velocities are pretty much right on top of each other, which is exactly what we would expect. And the forces, or the strains, are all over the place, which is also kind of what we would expect, considering that the piles are fairly flexible and that these hammers are running very fast. So the pile is almost constantly in motion one way or another, either axially or laterally, which complicates things. But one thing that we could also see in this record is this is about 150 milliseconds of data, but you could, through the visual inspection, see that there's about 110 milliseconds in between impacts. So if there was any uncertainty, we could clearly see these are distinct impacts that are applied to install these piles. And in this case, for this data set, the hammer is running at about 9 blows per second, which is really, I would say, impossible to keep track of unless you have measurements. I tried counting blows here in sets of 5 at a time, and just my brain just started short circuiting here. So we were able to see this in the data. We could always take the data, and certainly because the non-uniformity of these piles, especially that socket and spigot connection, we can model that non-uniformity in CapWAP for signal matching. And overall, we got a pretty good match. We could see that the non-uniformity can be modeled pretty well. We could assign resistances and get a total capacity. And overall, what we saw for the first 3 piles that we tested is we had capacities ranging from 65 to 75 kips, which is right here. And we see that 2 of the piles, T1 and T3, were driven to a deeper depth, while T2 was a little shallower. So the conclusions we got from our first round of testing is that the hammer appeared to operate with an energy transfer ratio, which is the energy measured in the pile divided by the rated hammer energy, somewhere between 23 to 38%. That's not great for a hydraulic hammer. That's more in line with a moderately maintained diesel hammer, but it's one of those things that we were able to see. The impacts were applied at a range of speed. So the blow rates range somewhere between 6 to 10 blows per second. Either way, it's a lot, but that's sometimes a factor of 2. So the penetration rate is really highly dependent on the operator themselves. They operate the speed of that hammer. They can put a certain amount of crowd force, and then they could also be in full control of the alignment of that hammer and pile, which is a really, really big component, certainly of the energy that's transferred into it. If we equate the number of blows, similar to how we do blow counts for driven piles, we are well beyond refusal condition for a lot of these piles. And that complicates things because the mobilized resistances that we got, 65 to 75 kips, notably are less than the 120 that they need. But we know that because these blow counts are really, really high, they're probably not the ultimate capacity. So we might be limited here about due to the hammer that we're using to apply these loads. So 2 days after we tested those piles and we said we don't have the capacity, but probably these are lower bound estimates, they ran a static load test, the contractor did. And the results, as you can see on the screen, showed that they went to 120 kips and unloaded it, and that line was almost linear. The reason they didn't go past 120 kips is something that occurs with static load testing at times, is the reaction piles started pulling out when they started going higher. So they had to terminate the test at 120, and clearly we could see that there probably is still reserve capacity above 120. These piles have more resistance. So we got called in to do some restrike testing to get a better correlation of the long-term resistance, to simulate and kind of see, compared to the static load test, what we have. So we hooked up our gauges. In the meantime, while we were gone, they poured grout inside of the piles, which is typically what's done. And then outside of the piles, they also poured grout near the head for about 2 or 3 foot. And that's more for lateral stability that they did that. So now we have a non-uniform pile. We have composite materials. We also have an enlarged area partially near the top. So the analysis was definitely complicated, but it's nothing that signal matching can't be used for. So in doing the restrikes, we were able to see we have higher capacities now, about 105 kips, 90 or 100 kips, still below the 120 target, but higher nonetheless. And that's in part to do with the increased stiffness, which is kind of what Les was discussing on his slides before. It allows us to transfer more force and try to attempt to mobilize more resistance if it's there. So from the restrike testing, we saw that the energy now is even wider in range. It could be lower even than what we saw. It could be even higher. So what's complicating this is also, again, the non-uniformity of the materials, the interaction of those materials, how they're transferring the forces and the loads. And again, it's very much operator dependent. The penetration rate may not be the best indicator of a correlating capacity, since it doesn't really account for the energy losses, the alignment of the hammer, the crowd force being used. So again, the blow counts were very high, even on the restrike condition. And so therefore the mobilized resistances were still probably not the ultimate capacities. And we had to note that. It's, again, a limitation of the hammer size. So we got called in, and essentially the contractor wanted to find out, well, what is the ultimate capacity on these piles? We want to know. And so we brought out one of our drop hammers, or Apple hammers here. And this is our second to smallest hammer. It looks big because these piles are fairly small. They're less than 6 inches in diameter. And so we were able to apply incrementally higher strokes or forces that were applied for dynamic testing here. And we finally were able to start moving some of these piles. So we could see T1 and T2A. Those are the shallower piles, probably in that sandy material. We could see that we have 145 and then 165 kips for those two piles. And you could also see the approximate pile sets that we have analyzed. It's almost 1/2 inch, and this is almost 1/4 inch. So we finally started moving these piles. These loads and capacities, that we're estimating are probably close to ultimate capacity, if not at there. The other two piles that were driven deeper, T3 and T3A, those have 265 and 300 kips that we were able to mobilize. And you could see the pile set was about 1/16 of an inch. So those piles probably are still lower bound capacities. There's probably more resistance that exists there that these piles can take, assuming that the stresses won't be high. And you could see the column on the right here for the compression stress, the second from the right. We had 55 KSI stress on some of these impacts, which is why we ended up terminating the testing at that point. So we were able to finally prove higher resistances and see them with a larger hammer. In doing so, we also realized higher strength of the shaft resistances. This is probably due to the additional time that the soil setup was able to occur, or the pore water pressure was able to dissipate. We also finally mobilized more end bearing, from 30 to 100 kips more. And we were at least finally able to say, oh yeah, all these piles do have above the 120 kips, if not double that in some cases. So the conclusions that we were able to get to is that we can say, and not just a GRL, but as an industry, is that dynamic load testing really is a feasible solution and can be successfully done during the installation of these piles. Certainly afterwards as well, in place of, if they can't be tested during initial drive even. The friction weld, that is something I was a little skeptical about. In the data, we could actually see that at the beginning of drive, we have two separate sections, like a broken splice or weld that we have seen before. And during installation, after a few minutes, that gap or those two sections basically form into one. And it certainly does look like it behaved as one section after that. So I was skeptical, but it really it performed as advertised. Dynamic load testing, again, depending on hammer size. If the hammer is a little small, we can only prove what we, as hard as we hit the pile, we could only see that much resistance. So if the hammer is size is a limitation, we would be only looking at a lower bound capacity. Could always have a bigger hammer come out to perform additional testing if necessary. It could be done after the piles are installed. Dynamic testing, as a general note, can always be used in conjunction with, or sometimes in place of, static load testing, like Les mentioned. We've had a lot of projects performed with dynamic load testing where it's just not feasible or physically possible to do a static load test. If your job site is 6 foot wide, for example, you can't put a frame there and at least do it in accordance to ASTM, a static load test. And the pile installation time is highly dependent on the energy transferred, as is always the case for any driven pile, but more so for this application because the hammer alignment literally changes with depth. As the operator lowers his the hammer down, the alignment changes every couple of seconds. So it's very sensitive to those changes. And maybe as an overall conclusion, we can again say that we have been able to obtain reliable and conclusive correlations so far, and we hope that if there are other opportunities or capability of testing more of these types of piles in the future, we can only improve the method and improve the confidence that we have in these types of piles and the usages of them. And with that, I will say thank you and hand it over back to Travis.
Thanks, Alex. And thanks to you as well, Les. Very excellent presentations. If you have some questions, there's still a little bit more time to get them in. A few questions I have here. Alex, do they ever apply any tension load to these because of that friction joint?
That's a good question.
Okay.
I asked that question. Apparently, the answer is yes, and I've been told by the manufacturer that the piles perform well. I did not test them under tension. I would have loved to, but maybe in the near future I could be more involved. But I'm told they perform well.
Okay. Okay.
Travis, I've seen before where they've actually dropped the bar and grouted them to get some tensile capacity.
Yeah. Okay. That makes a lot of sense.
Yeah, there was a center bar that they put there, right, with the grout. Yep.
Les, you made a lot of your comparisons were based on a percentage of the yield strength of the steel. Do any of your local code groups allow for considering higher yield strength steel? Like, can you use 60 KSI steel to increase those
well,
loads?
they have limitations of like Connecticut had 24 KSI. If you can have 55 or 60 KSI high grade H piles or something, they would let you use it as long as you're under that 24, right? Massachusetts,
you can't go higher no matter what, right?
Massachusetts was 16 KSI. So in order to get around that, you have to go to another section in the code that allows you to justify the higher stresses, which isn't a big deal because it's just saying you need a load test, you need geotech report, which almost every job has. So it's kind of seems like to me almost automatic. But then you can go up to 32 KSI, which I haven't seen anyone go that high.
Yeah. Wow. Actually, on that same note, what do you a lot of the discussion was hard driving or driving into rock. What do you see as far as stresses at the toe relative to stresses at the head or the static stress?
Well, for weathered rock, I showed that one case where the toe was lower because there was a lot of friction on the pile. So, it was in the 20s to 30 KSI, where at the top it was 30 to 35 KSI. When it becomes short pile with high loads, then you could have stresses that could exceed the top of the pile. And that could approach, higher values of 40 to plus KSI or even higher. The thing I didn't mention was that for H piles and other pile types as well, but we measure, especially with the PDA, we measure the stresses and it's based on an area. But if we're in pinnacled rock or uneven sloping rock and we have 50% contact on that rock, all of a sudden the stress is doubled. So that's probably a lot of reasons why the piles rip and tear and twist, because they're encountering just a portion of that contact stress, and then the stress is double or triple. So just an observation.
So here in the Midwest, it's a lot of hard rock. There's not many weathered rock conditions, and I'd say the toe stresses are maybe 30% higher than the pile head stresses or something like that. We don't have very long, not extraordinarily long piles or big weathered rock conditions like that. Hey, Alex, you talked about mobilization of kind capacity, what is the movement that you need or that you would consider that pile capacity mobilized?
Yeah, that's a good question. I mean, typically for driven piles, anything less than 10 blows per inch equivalent is typically considered probably geotechnical failure, or mobilized resistance is equal to ultimate capacity. Once you get past that practical refusal condition, which is 10 an inch, typically in the industry, you're probably under predicting, but you don't know for sure, which is the uncertainty aspect there. You might be there, you just or you might not, so a lot of times if there's a concern, if you have, say, relaxation or something like that you're worried about, having a high blow count might not it might not be a confidence builder. So additional testing might need to be done, but that's usually the threshold, somewhere around 10 blows an inch equivalent, or a tenth of an inch movement usually is what we look at for most driven piles.
Okay. I have a question for you, Les. It's sort of detailed. I'm just going to read it to not shortchange anything. Regarding tapered tubes or monotube piles driven in glacial deposits of JFK and other New York areas, have you seen difficulty with large diameter taper tube piles installed in pile groups? Would you recommend a greater spacing than 3 diameters as the tubes get larger in diameter and the pile groups become larger?
Yeah, I am reading that. I do see it.
Oh, you see it.
So, yeah. So
wish you would have told me.
right. Yeah. Well, that's good. I mean, it helps a little bit, but so what applies to taper tube is also similar for pipe piles. We've seen both have heave problems, and then usually the contractors work from the pile cap and in go outwards, so they don't trap themselves and densify the soils. So they do sometimes go with greater spacing, but I think it's also happens on pipe piles as well.
And do you see that what's described here in this last sentence, difficulty getting them the same depth as you move on?
Right. And that's why they go from the inside of the cap out as much as they can to try to minimize that. And I've seen even that doesn't work sometimes, and they have to pre-auger or pre-drill a portion of it.
Do you find that they work inside out as they're supposed to?
Oh yeah, these inspectors in New York, they make them do that.
Okay.
Yeah.
Some of the places we work at's the code, but I don't know that
Right.
anyone actually has that in their head to do.
Yeah, we've seen that as well. We've done a lot of work in JFK and all over. Densification is a real thing. Sometimes it's good for soil resistance, but it's bad for actually getting the pile on the ground. But having the tapered section in a way kind of helps also, because it's a reduced area a little bit. So it's a little, less displacement of the soil, less densification towards the bottom, but nonetheless, it still occurs. So, yeah. Okay, well, if there are no more questions, I think that we're going to end the Q&A now. Thanks again to both of you for the time presenting here today. This webinar is presented every other third Wednesday of the month. So that means the next one will be the 20th of September at the same time. We're excited to have Dr. Rick Kaufman from University of Arkansas. He has a lot of research focused on pile foundations subject to liquefaction and down drag loading on piles. So hope to see you then. And thanks to everyone for attending.
Thanks, Travis.
Thanks a lot, everybody.
Bye, all.
Thanks again, guys.